So at the end of last time, we just been looking at series in extended real line and seen that they behave fairly well. We'd also observed that it looks like there was some sort of a problem with the algebra of limits, which we will revisit now. So we're going to have a look at the extent to which the algebra of limits does work in the extended real line, especially non-negative extended real numbers. Now, as with most of the stuff here, I won't go through many of the proofs in great detail yet. I'm going to start to do proofs in a bit more detail when we get to collections of sets, and when the material gets a bit more abstract and a bit harder, and I'll do some proper proofs there. But here, algebra of limits, we already know that works in the real line for, if you've got two convergent sequences of real numbers, then you can add them term by term and get another convergent sequence of real numbers, and the limit is what you expect, and the same for multiplying them term by term. So now you try the same thing in the extended real line, and, well, there would be some issues if you were working with negative extended real numbers, because you're not allowed to add plus infinity to minus infinity. But we're not doing that. We're working, just for the moment at least, we're working only in the non-negative extended real numbers, so there's no problems with addition, and as a result there's actually no problem at all with the algebra of limits for sums either. It's only products here where the problems arise. So if you want to use the usual algebra of limits to deduce the new algebra of limits, what happens is you've just got a few extra cases to consider. And I've almost given you enough information already with that sandwich theorem I gave you last time. Essentially, if you've got two sequences of of non-negative extended real numbers, and they both converge to a real number, then what actually happens is after a while both the sequences will consist only of real numbers, and you'll just go back to the usual algebra of limits for real sequences. But if either of these sequences tends to plus infinity, then xn plus yn will be at least as big as xn and at least as big as yn. So if one of those two sequences goes off to infinity, then the bigger one has to as well. So you just get it directly from the sandwich theorem. So it's sort of two cases. One, either of the sequences tends to infinity, then you get it from the sandwich theorem. Case two, both of the sequences converge to some non-negative real number. In that case, you say, well, okay, there might be a few infinities in there, but it's got to leave infinity eventually and stay away from infinity. And then you look at what's left of the sequences, and it's just two convergent sequences of real numbers. And you already know about those. You're allowed to quote the result for real numbers. So it's just, again, a little bit of a boost up, and it works, and it's fine. So that's no problem. You can check the details as an exercise. So the problems come for products. And we already looked at 1 over n. Oh, let's have a different colour. We already looked at 1 over n times n equals 1, which tends to 1 as n tends to infinity. But 1 over n tends to 0, and n tends to infinity, and 0 times infinity equals 0. Okay, so that's one problem. Also, infinity times 1 over n equals infinity, and that tends to infinity is not equal to infinity times 0. So why is that a problem? Well, if you think of infinity as your alpha, or as a constant sequence, whichever, and your 1 over n as tending to 0, then your algebra of limits has gone wrong again. So even constant multiples of sequences go wrong if your constant multiple is infinity. And even if you aren't multiplying by infinity directly, as in 1 over n times n, you end up with a problem in the limit with 0 times infinity. So the algebra of limits of products doesn't quite work as it stands. as long as your alpha isn't infinity, you can do constant multiples and you're okay. That's the only problem with constant multiples is if alpha is infinity. Alpha equals naught is a special case, but fortunately naught always wins, so you're okay. So you can check that all the other alphas, except for infinite alphas, are okay. But there is a problem, and the question is, how do you fix it? And the answer is that you have to restrict attention to which sequences you want to do the order of limits for when you're dealing with products. So restrict attention to non-decreasing sequences. So what are we going to do? We're going to have x1, so naught less than or equal to x1, less than or equal to x2, less than or equal to x3, and so on. And that any non-decreasing sequence has to converge to something. And you have the same for y. Then the order of limits now does work when you get that xny tends to xy. Of course, you also have that it's non-decreasing. So naught less than or equal to, let's get this right. Naught less than or equal to x1, y1, less than or equal to x2, y2. And it does tend to xy. So the order of limits is okay, as long as you're careful. You can't do any on monotone sequences because the 1 over n was monotone but decreasing and gave us trouble. Even with the constant sequence infinity, which is also monotone decreasing, or non-increasing. So if you're working with non-negative extended real numbers, you should work with non-decreasing sequences, monotone increasing sequences. If you're going to work with negative extended real numbers instead, or non-positive extended real numbers, then you would want to work with decreasing sequences if you want to do the product instead. And that's how that would work. Well, it's an exercise to check it, but I'll give you some hints. Here are some cases. If neither xn nor yn tends to infinity, then it's just the order of limits in R. Right, so if neither of them tend to infinity, then it follows from the order of limits in R, because they're all real numbers. Usually what you would say is if they tend to a real number, then after a while they're real numbers. But actually in this case, since they're non-decreasing sequences, if they don't tend to infinity, then they never, not only do they not tend to infinity, but actually in this case none of the terms at all will be infinity either. Because if a non-decreasing sequence hits infinity, it gets stuck with that. So you just get the completely ordinary order of limits in R in that case. So we can assume at least one of them tends to infinity. But there is one more special case. If either of the sequences tends to 0, then it actually has to be constantly 0 because they're non-negative numbers. If either sequence tends to 0, then because it's non-decreasing and it's non-negative, then it must actually be the constant sequence 0. And then that's an easy special case. The remaining cases where neither of them is constantly 0, so they both leave 0 eventually and never get back anywhere near 0, and at least one of them tends to infinity. And that final special case you could do with a sort of comparison test, something you'd have to work out, some sort of comparison test, or sandwich theorem, or deal with it directly by m's and n's. So the remaining case both sequences eventually leave 0, and at least one of them tends to infinity. That will leave 0. So then you have to prove that x, n, y, n tends to infinity. It's probably best to go back to the original definition to prove that. The one in terms of m's and n's. Or you could prove separately some result about constant multiples by non-infinite multiples, which would be would require something like that. So you could prove a result about constant multiples separately and then use the sandwich theorem. That would also work. I'll let you fill in the details however you like on that one. So this is absolutely crucial when it comes to some of the theory. We may not get to all the theory I want to get to, but if you want to get through any of the integration theory and so on, you will absolutely, it's absolutely essential that you know that you can work with monotone increasing products like this, because you need some sort of algebra limit still, even though we've lost the fully general algebra limits for products, but you need something still in order to do any sensible work at all. So this is what we've got left. Any questions about the algebra limits? I think that's the end of the algebra limits section. Would you like to say anything more about any of the algebra limits? Okay, well, the main thing, sort of, because when I don't give you the proofs, that means the proofs are not examinable as bookwork. But of course, things can come up as unseen or on assessed coursework or something like that. And anything, of course, any work you do in filling in the details will help you to understand this stuff better. So it's all worth filling in if you can do it. But if you want to just take my word for it and believe the results that I've stated, then that will be sufficient for understanding the syllabus, even if it doesn't get you as fluent as possible with all the material. You'll still have enough to be able to follow the notes. Right, so let's stop that recording there.